Assalamu alaikum. Today we are going to find the capacitance of an isolated spherical conductor. Usually when we are calculating the capacitance, we have a couple of conductors. But in this case, we want to find the capacitance of a single isolated spherical conductor. So in this case, to find the capacitance generally, we are using this relation. The capacitance is equal to Q, which is the charge, divided by V, which is the potential. Okay, and in this problem, we want to find the capacitance for this isolated spherical conductor. So before starting calculating, we must determine the radius of this spherical conductor. This is sphere, it's not circle, okay? Let's say that the radius of this sphere is equal to A. We all know that V is the electric potential of these two conductors within capacitor system, but in this case we have only one conductor. So for this we are going to construct a hypothetical imaginary conductor which has a negative sign, which has an opposite charge of this capacitor, okay? This conductor, I mean, that I draw has the same charge of this conductor, but its sign is opposite to it. So as it's positive, this is negative, okay? And in order to make the impact of the potential due to this negative hypothetical conductor to be zero, okay, we assume that this spherical conducting shell exists at infinity, okay? The reason of this is that the potential at infinity is equal to zero. Now let's start solving by determining the electric potential difference between these two conductors. Okay, for this we are going to take the negative line integral of the electric field. The bounds of the integral is infinity, okay, which is the reference point, and it's the location of this hypothetical negative conductor, okay, and A, and as infinity is the radius of this hypothetical conductor, negative conductor that I draw, and A is the radius of this isolated spherical conductor right there, okay? Now what is the equation of the electric field? The electric field originated by this spherical shell is equal to the most basic equation we all know about the electric field, which is Q, which is the charge inside this spherical shell, divided by 4 pi epsilon, where epsilon is the product between epsilon sub 0, the permittivity of the free space, and epsilon sub r, which is the relative permittivity of the electric, times r, okay, r, which is the distance between some point, okay, let's say that this point P, and the spherical shell, okay, and the surface of the spherical shell, I mean, okay, the distance is r, okay, dotted with dl, and dl is an arbitrary differential path which has components at 3 coordinate system, and in this case I am handling the spherical coordinate system because it's so obvious that it's the most suitable in this case, as we have in this case a spherical conductor shell, okay, and the electric field as well is radial, is directing along the radius. The electric field is directing along the radius of this spherical shell. So the differential length, which is equal to the summation of the components from the 3 coordinate system, which are the radial component and the azimuthal angle component and the polar angle component. These two are going to vanish due to the dot product with E, and this will still alone, okay? We will end up with the radial component, which has the unit vector of A sub r times dr, which is the differential length along the radius of the shell. And I'm going to eliminate this negative by changing the order of these bounds. Okay, now we can do this integration. We all know that the integration of 1 over r squared is equal to minus 1 over r. Now let's do the integration. Okay. Now what we will do is substituting infinity and a for r in this equation, and we will end up with, okay, and this is the potential, and this is the potential difference between these two conductors, or by other words, the potential due to this isolated spherical conductor shell. Now let's find the capacitance of this spherical conductor by applying this relation. Okay, and this is the capacitance of this isolated spherical conductor. It's equal to 4 pi times the permittivity, now times the permittivity of the dielectric surrounding this spherical conductor, times a, which is the radius of this spherical conductor. We see that the capacitance is dependent of the dielectric surrounding this conductor and the geometry of the conductor, or by other words, the radius of this conductor. Okay, that's the end. See you.